probably one of the last times that you talked about concavity was whenever you were learning how to graph a parabola. Your teacher may have said that a graph that turns up is concave, concave up, and a parabola that turns down is concave down, and that is true. With calculus, if we are having trouble determining if a section of a graph is concave up or down, then this is helpful. If you start drawing in the tangent lines and the tangents are all above, that is not right. It's concave up. If the curve, okay, I read that wrong. If the curve is above all of its tangents, if the tangents are below, that's what I was trying to say, your tangents are below the curve, then it's concave up. And it's concave down if the curve is below and the tangents are above. So concavity is what we're going to be talking about, and we're going to determine from an equation whether a graph is concave up or concave down, which in turn will help us sketch a better graph of our function. So just like we've been finding critical points, or the places where our graph changes from increase to decrease or decrease to increase on the first derivative number line, we're going to do that same sort of thing to determine points of inflection, because points of inflection come from our second derivative, and they're going to be the points where the curve changes its concavity. So here we have a critical number, but here we have a point of inflection, because we go from concave down, tangent lines above, to concave up, tangent lines below. So anywhere that the graph changes concavity, we have inflection points, just like we have relative maxes and mins whenever we have a change on our first derivative number line of increase to decrease. So let's take a look. In these graphs, we're just going to talk about concavity. So here, the graph is concave down in all of this, but somewhere in here it switches from being concave down to concave up. So therefore there is a point of inflection right in there where it changes concavity. In this graph, this entire thing is concave up. So this graph doesn't have a single point of inflection, nor does this graph, because in neither of these graphs does the concavity change. The concavity has to change in order to have a point of inflection. So on the next page, they're going to explain to us how we're going to know, using our function, whether or not our graph is concave up or down. So here's what it says. We want to be able to take the derivative 2 times. The function must be twice differentiable in order for us to use the concavity test. And if our derivative has a section where it is positive, then it's concave up. If our second derivative is negative, then it's going to be concave down. So anywhere that our second derivative number line changes sign, there's a point of inflection, and it will change from concave up to down or down to up. So it's very, very similar to increase and decrease. So we're going to do all of those things that we've already talked about. First of all, we're going to find our intervals of increase and decrease, which require the first derivative. So for part A, I need my first derivative. So I have 4x cubed minus 12x squared. I'm going to set that equal to 0, so I need to factor it out. I'm going to factor out a 4x squared. It leaves me with x minus 3. So x is 0 and x is 3. All right. For increase and decrease, we need to put those on our number line. This one doesn't give us a specific interval, so it's an open interval. We're going to put 0 and 3 on here. We're testing on the first derivative. And so when I put a negative number in here, so like -1, this is going to be -1 times 4 is -4. Negative in here would be positive. So -12, -4 minus 12, that's negative. If I put in like 2, that would be 8 times 4 is 32. Over here, positive 48, so -48. So this is going to also be negative. This number is bigger than that one. So over here, if I do 4, 4, that's 4 to the 4th power. This is 4 squared times 4 times 3. This one's going to be smaller than that one. So, and that's all I'm trying to determine, which is bigger, which is smaller. I'm kind of cheating a little bit because I'm not actually figuring out the numbers, but if you can figure out which one is bigger and which one is smaller, that's all you need to know so that you can know whether you're going to end up with a positive or a negative value. So what we have now is intervals of increase and decrease. So my graph is going to be increasing from 3 to infinity, and it's decreasing from -infinity to 0 and from 0 to 3. I can't include 0 as a place where it decreases because the graph was actually, the derivative was 0 at that point, not negative. So only the places where it's negative. This is a place where it was actually 0. So be sure you separate those intervals there. All right, then it asks us to find our relative maxes and mins, and so we can also determine that here from this number line. We go from decreasing to increasing, so this is a relative minimum. I have a relative or local minimum at x equals 3. And I don't have a relative maximum on this one. Now, if they want the value, you would need to put the 3 back in to your equation. So 3 to the 4th power minus 4 times 3 to the 3rd power. Here, would be 81. I don't trust myself. Hang on. -27. So if they wanted the point, you'd need to put it back in. You get 3 -27 is the actual point where we have a relative minimum. But if they only ask for the x value, that relative minimum, you could just do the number line and be done at x equals 3. But there is no maximum. There's no relative maximum. I guess, well, it also set out here to justify each of these, and we've had some trouble justifying, so let me back up a minute here before we keep going. Whenever you're justifying the increase, you're going to say that it is increasing because the derivative is positive. Or you could say f prime of x is greater than 0. But you have to list f prime of x, that's going to be something they're looking for, and something about it being positive. This section of the graph is decreasing because the derivative, you can't just say it, because the derivative is negative, or because f prime of x is less than 0. So you can say it either way, but you have to state the derivative and negative. Then for the relative minimum, we're going to say that this is a relative minimum because our derivative changes from negative to positive at x equals 3. Okay, so now we'll keep going. C wants us to do intervals of concavity. So for intervals of concavity, we need our second derivative. So the second derivative is going to be 12x squared minus 24x. I just take the derivative of what I had right here. So I also need to find my possible points of inflection the same way I did my critical numbers. I'm going to set this equal to 0. So I can factor the 12x out, leaves me with x minus 2. Set that equal to 0, get x is 0, and x is 2. And I'm going to put that on the number line, but this time it's my second derivative number line. Sorry, probably couldn't see that. All right, again, it's an open interval, so I'm just going to put 0 and 2 on my graph, and then I'm going to test the points in the second derivative. So I'm going to put negative, like negative 1 in here. So negative 1 squared would be positive, so this is positive 12. Negative 1 in here would make this positive, so that's a big positive number. If I put 1 in, this would be 12, and this would be negative or minus 24, so the negative number is larger. And over here, if I put in like 3, 3 squared would be 9 times 12. What would it be? 108. And then 3 times 24 is smaller, so that's going to be positive. And so here I have a graph that has to do with concavity. What it says up there is that if my second derivative is positive in any section, then it's concave up in that section. So this graph is going to be concave up from negative infinity to 0, and again from 2 to infinity. This graph would be concave down from 0 to 2, because that is where the second derivative is negative. So that's going to be our justifications over here. To justify this, we're going to say it's concave up because our second derivative is positive, or you could say because f double prime is greater than 0, and we have concavity down whenever our second derivative is negative, or our second derivative is less than 0.